Yeah, hi, I'm Jeff Moore. I think I know everybody in this room, but I'm going to do my own introduction because why not? I'm from Tucson. I went to the University of Arizona. I have a geological engineering degree from there. After that, I went to the University of California, Berkeley, and I have a master's there in civil engineering and geotechnical engineering. And at the time, I also obtained a second master's in earth science. I was sort of transitioning more to geoscience work during that time. And then, of course, PhD, which was in civil engineering. From there, I went to ETH Zurich. I was a postdoc for 2 years, and then one of what they call an over assistant there, which is like a limited term. Job duties akin to an assistant professor, but without the chance of tenure. And then I came here, arrived here in January of 2013. So I'm reflecting that it's basically been 10 years. And it's basically been 10 years that we've been working on this project. This was something, that I had sort of dreamed up when I was leaving Zurich and looking forward to coming here, came out of the work that we were doing in Zurich. And so, yeah, when I was putting together this talk, I was also thinking that it's kind of like, 10 years of working on this subject and how far we've come. When we first started, we didn't know if any of what we were going to do would work. And so from just that like initial first measurements up until like now, it's been kind of fun. I also realized that the headshot that got circulated is also now exactly 10 years old. That was shot on my balcony in my apartment in Zurich at like 9 in the morning on a Sunday. And, in the great academic tradition of out-of-date headshots, I'm planning on keeping that one for another at least like 10 years or more. So, yeah, welcome to also alumni and online guests. I can sort of see you here to my right. So let me fumble here. Over the years, this project's been supported by a number of NSF grants. I'm really grateful to program coordinators for their support. That's both through the Geosciences Directorate and through the Engineering Directorate. And a lot of what you're going to see today comes from the PhD projects of Paul Geimer and of Riley Finnegan, current NSF supported work being worked on by Aaron Jensen. And we have benefited during this time from a lot of really valuable contributions from GG undergrads, master students, MISTY students. There's 3 MISTY names in that list, postdocs, and of course, some of our seismology faculty here in the department have really helped me keep this project grounded in seismology fundamentals. So, Utah is, of course, home to some of the world's most dramatic and beautiful, iconic desert landforms, red rock landforms. Here you see Eagle Plume Tower. It's located in Valley of the Gods, which is in the southern part of Bears Ears. And by now, most of us are very much used to seeing these landforms in beautiful photos like this. This was taken by Riley from a drone. However, we think, one thing that's missing, this is a portrayal of a landform as static. We as geologists are pretty good at like visualizing landforms evolving over long periods of time. We would like to add a layer into that kind of dynamic view as the now. So we would like people to be able to see geologic landforms looking something a bit more like this. Here you see the first 4 modes of vibration of Eagle Plume Tower. Of course, greatly exaggerated, but nonetheless representing a very real phenomenon that's ongoing. Similarly, most of us are used to hearing geologic landforms like this, but we would like people to experience these landforms as sound. And if you'll bear with me, I'm going to ask for 36 seconds of your life. And I need to make sure I mute my microphone. Thank you for your patience. You've just heard 1 hour in the life of Barrette Arch. That's 1 hour of ambient vibration data sped up 100 times to become audible. That's 3,600 seconds becoming 36 seconds. So today in this talk, I need to get back to that screen. The main purpose is to tell you how we got here and what can we do with this information. Before I do that, I want to give a really brief primer on structural dynamics. And here you see a picture of the Campanile Tower on the Berkeley campus. It's 94 meters high. And you're seeing what is a very old measurement of the natural vibration of this tall tower. We've known from structural engineers for more than 100 years that tall buildings and bridges are constantly in motion. They are swaying, bouncing, vibrating, twisting at what are referred to as their normal modes. When these modes are excited by ambient forces of the earth, as like wind or ambient seismic energy, we might refer to this as ambient resonance. These ambient sources are exciting resonance of the structures at their normal modes. So here you see the Campanile Tower in the east-west direction and the north-south direction. It's more or less this kind of full height bending of the tower. It's very much like a cantilever, and it happens at about 0.8. We hypothesized early on that natural landforms are doing the same thing, but we didn't know if we'd be able to measure it. So here you see Castleton Tower. It's about 110 meters high and also has a first resonant frequency, the fundamental frequency of also about 0.8. So these natural frequencies of any structure are very simply controlled by the geometry and material properties of that structure. And if I look at the material properties, there's really only two things that matter: stiffness and mass, or if you like, density and Young's modulus. So if I am able to measure the natural frequencies, then I can establish what you might think of as something like a structural fingerprint for the landform. And this procedure of measuring and describing these natural modes is what we call modal analysis. So here you see Castleton Tower again now run through a calibrated numerical modal analysis, and we see a clear view on the 3D displacement field for Castleton Tower. At its first mode, 0.8 hertz, it's full height bending against the slimmest dimension of the tower, slimmest horizontal dimension. Second mode is full height bending against the thicker horizontal dimension of the tower. So these are more or less mutually perpendicular bending modes. Again, quite like a cantilever, very well described by Euler-Bernoulli beam theory, if you want that information. So modal analysis is at the heart of everything we do. It's actually great fun and really cool. And we had a lot of success with it, so we really enjoy doing it. In order to do this, I just want to describe, how we do this and how we kind of work through the data. So to do this, we generally we often use compact broadband seismometers. They're 3-component instruments, 2 horizontal components of motion, 1 vertical. Trillium compacts are usually what we use. About yay big. You simply need to set them on the arch, and that can be in the middle of the span, that can be on the side, whatever you like. And then we often cover them with this bucket. Allison picked up those buckets at Walmart 10 years ago. They're now painted brown, but we're still using them. And that just keeps wind off the sensor and helps lower the noise floor. So here you see Allison setting up this is surprise arch in fiery furnace area of arches. Really cool arch. You kind of walk through here and then, it's a surprise. And there you see Paul working at landscape arch. Of course, we don't want to go on the lintel at landscape arch, so we're able to actually measure down here at the bottom. And of course, we have permits with the Park Service, which is a whole ordeal. Very much worth it. We've had very valuable cooperation with them over the years, but it was hard to obtain these. So we're looking to record continuous ambient vibration data for a minimum of an hour, we like, and it can be anywhere then 24 hours. We can keep going. Sometimes we have 3 years of continuous data from one site. A couple more photos because it's fun. There's Riley on Barrette Arch, which you heard a minute ago. Most of the time we can just walk out onto these features. We don't need to be in the middle. We like to be in the middle, but we don't have to be. We can be on the side. This one, it's really easy to just walk out there. That's me and Ben White on Rainbow Bridge back in 2016. And of course, there we had to just rappel down onto the bridge. So every now and again, it requires some technical access, but most of what we do is non-technical. Big shout out, however, to those folks that have helped us with technical access over the years. Ben White, Jackson Bacher, you might remember those names, some of the faculty in this room, some of our great undergrads. And then Kat Vollinger, shout out to her. She's a seasonal ranger at Rainier, a climbing ranger at Rainier, and writes me when she's coming through and says, hey, do you have anything that you want me to measure? And I just dream up something wild. I'm like, yeah, can you, climb the valley of the Eagle Plume Tower? Or I asked her to do Castleton Tower, just hard and wild things that I'm dreaming about. And she said, okay, yeah, I'll do it. And she just makes it happen. So Kat's awesome. What to say? In the time domain, ambient vibration data don't look like much. They're not very exciting or very informative. You might see an earthquake, but beyond that, you're not going to see much. The data come alive in the frequency domain. So here we see power spectral density. We have power on the y-axis, frequency on the x-axis, and we're looking at the two horizontal components of motion for one sensor in red that's located on Rainbow Bridge, and then the trace in blue is from a sensor that's about 200 meters away on the canyon floor. So this is what we might refer to as a reference instrument, just somewhere off the feature, but located nearby on bedrock. And in the frequency domain, now here what we're looking at is this vibration spectrum, this ambient vibration spectrum. And for analogy, you can think of it like a guitar string. If I simply pluck a guitar string and analyze the sound produced by that string, I would see in a sound spectrum, a fundamental mode, which is the string going up and down. I would see also another sound that's at an integer multiple of the first one at frequency, which is the second mode, and another one, which are higher and higher order modes. And it turns out rock arches and towers are doing the same thing. So here we have, a first mode spectral peak measured on Rainbow Bridge, 1.1 hertz, the next 2.2, 2.5, 4.2, and so on. We also have spectral information recorded equally on the bridge and on the canyon floor. And for example, this energy at about 0.2 hertz is what we call a microseism. It's global seismic energy created by the Earth's oceans. We see that in almost all of our data. And it is something that is, of course, recorded equally on the canyon floor and on the bridge. So from this ambient vibration spectrum, we have a kind of hypothesis generated that we're measuring the natural modes of vibration of Rainbow Bridge in this case. What we want to do now is carry that hypothesis forward and test it using numerical analysis. So our workflow has kind of grown to be more standardized over the years. It starts here. We use ground or drone-based photos to make a 3D model using photogrammetry. And here you see Rainbow Bridge. We then take that 3D model, trim away the extra bits we don't need, fill in any holes, turn it into a 3D solid so that we can import that into a commercial finite element software package. We use ComSol Multiphysics. You could use many other things to do this, where we perform what's referred to as eigenfrequency analysis to simulate the natural modes of vibration. So eigenfrequency analysis doesn't use any input or time domain analysis. It's entirely frequency domain. So you don't have to give it white noise or some kind of wavelet input like that. It just solves for the distribution of mass and stiffness across the geometry you've given it and predicts the natural modes. Important herein, we, for all of our models, use isotropic uniform composition. And I hope to convince you by the end of it that we get away with that. Certainly that's an assumption, but it works pretty well for most of these arches, which are in uniform materials, like Navajo sandstone here. Okay, so we have a numerical result, which we're looking to then match to our field data. And the matching consists of two things. We're looking to match the frequency, the natural frequencies between the measured and the model values. And of course, then we're looking to also match the polarization information, or what I refer to as the modal vector. So the sensor on the bridge, which is about here, we can query the polarization information at different frequencies, and that shows us how the bridge was moving at that frequency at that point. And we can do the same from our model. We can sink a point here in the model and then ask, how's the bridge moving at this point in the model? So we're looking to match frequencies and modal vectors. And if we do so, we can arrive at something that might look like this. This is a rainbow bridge again. This is a good result if you're looking for that qualitative description. We have successfully matched between our experimental data and our model 7 of the first 8 modes of vibration for the bridge. So you see here the measured frequency, the modeled frequency in each of the titles. And then in the inset stereo plots, you see the polarization vector. And, so the measured is open circle, modeled is closed circle. So we have a really good match between frequencies and displacement vectors. In case you're wondering, this is the mode we missed. It's mode 6. It's kind of a torsional mode. I don't know why we missed it. It might not have very high energy, and so it might be hiding beneath or near its neighbors, but that's what we missed. So when we have a result like this, we now have, number one, kind of validated the hypothesis from our experimental data that those are, plausibly the natural frequencies of the bridge. Number two, we have a really enriched view of the modal displacement field, because in almost all of our sites, we basically only can put a sensor on like 1 or 2 or 3 places. Here, we could put a sensor here, but we're not allowed further on the bridge for safety reasons, which is fine. And so that was it. That was all the information that we could get in. So now we have this rich view of the displacement fields. We can also predict the strain fields at any given mode and frequency and so on. So we do this a lot. Here's Eagle Plume Tower again, which you saw in the animations. Again, this is the measured. This is the modeled frequency. I switched the color scale. Sorry for that. That's a evolution over the years of the project. Now blacks are maximum displacement and sort of clear or unshaded is minimum displacement. So the base of the tower is basically not moving at all. In most of these up until it starts to evolve here. And again, we're matching the modal vector. There's the sensor that Cat placed on the tower. And we have the data, and then we have the modeled deformation. These are shown again as stereo plots or polar plots, whatever you like, of those modal vectors. And so we're doing a pretty good job matching. Some of these are really precise matches. This is a torsional mode. The tower's second mode's torsion here, and the match to frequency is less good. Match the modal vector is very good. Nonetheless, in the whole, we would say, okay, that's a good match. We're satisfied with the match. The model is reproducing the data. Therefore, we can take a look to the model and say, okay, here's what the modes probably are, more or less, given some uncertainty. So as I mentioned, we've done this a lot. We published 2 compilation papers. This was published by Paul Geimer. It's 17 arches where we've achieved this good match between data and model. And we have the arches arranged according to size. So the largest ones down here have the lowest natural frequencies, and the smallest ones up here have the highest natural frequencies. So generally, we're looking in the range between like 1 and 40 hertz. We did the same things for towers. This was a compilation paper led by Riley Finnegan. Now we have frequency on the y-axis, and towers again arranged from largest Castleton Tower to smallest. And we made a real effort to try to find some real dinky small towers, even though they're not very impressive. We wanted to get something in the small range, hoping to kind of validate this like cantilever analogy, and we were able to do that quite successfully. So, we're looking at a very close match between frequencies and the polarization vectors for these 10 towers. We do this at other places too. This is the Courthouse Mesa instability. It's located near the Moab airport. And there's about this 500-meter long crack running along the mesa top here. Here you see the south end. This is a site, focus site for Aaron's PhD work. And there's Aaron directly there. I promise it's not as dangerous as it looks. And so we have this great slab, which is, up to 70 meters deep, that's kind of peeling away from the cliff. And in this case, it was really interesting because we had such great access to the length of the slab. We actually could put out, I believe it's 24 of these nodal geophones along the length of the slab and actually measure the modal deflection patterns. So we could directly measure the mode shapes and then use our model as typical and conduct a kind of manual inversion procedure where we try to match our model to the measured mode shapes by adjusting the boundary conditions. And in doing so, arriving at the best match, we get this calibrated picture of what the boundary conditions in the crack are at depth. So how deep it is, how deep is the crack all along the strike, which is information that I challenge you to find another way. It's quite hard information. So we think it's a cool technique demonstrated here at the Courthouse Mesa site. Yeah, we also did the Matterhorn because why not? We had this hypothesis that mountains should show the same kind of large scale modal deformation patterns, and we should be able to conduct this similar kind of modal analysis on mountains. We know from engineering seismology that topographic amplification occurs in part due to resonance of topography. So we thought, well, let's measure this and let's measure it in the king of topography, the Matterhorn. This was something I did while on sabbatical. Jan Boytel here, second author, he'd been working on Matterhorn, this area, the Hornley Ridge, for 10 years. And so, I just pitched this idea to Jan and he said, okay, yeah, let's do that. Sounds cool. And Jan then set up a seismometer in the Solvay hut, which is here. That's still running, it's still there. If you want the data, you just get it. And then they also set up a seismometer on the summit of the Matterhorn, Jan and Sammy Weber, which ran for 3 months. I joined for setting up the reference instrument, which also ran for about 3 months. And so that was our array. And from that information, we were able to conduct the same, matching the data, identifying these natural frequencies and then matching the polarization vectors, and really then getting this understanding of what are the first, here you see the first 2 modes of vibration in Matterhorn. Similar in ways to other things we've seen, it's vibrating back and forth at these sort of mutually orthogonal directions. If you're curious about what a seismometer on the summit of the Matterhorn looks like, that's Sammy setting it up. They flew up there in a helicopter and stood out with all the stuff, and the summit, is this kind of narrow ridge, and so it must have been quite exciting. Got all their stuff dumped out, worked up here. This thing streamed data, had internet, continuously streamed data, really dramatic and perfect. I was invited to come. I didn't. I knew I wasn't going to be any help. I would just be sitting there terrified and sort of unable to actually do any work, useful work. So really cool network setup. Okay, that's a lot about modal analysis. So why are we doing this? There's 3 main topical reasons why, which I'm going to walk you through in the next slides. The first is structural health monitoring. That was really the impetus behind this project at the outset. That relies on repeat measurements of this structural fingerprint to try to identify structural changes. The other big reason, and this is really the subject of Riley's PhD, is this topic of vibration risk assessments. And here we're starting with the idea of resonance susceptibility. Certain energy sources might be able to excite resonance of these landforms. And when resonance is excited, then we have the sufficient energy transfer between the source and the receiver, and we have higher amplitude vibrations, higher amplitude stresses that could lead to damage. So we've been looking at a number of different anthropogenic energy sources and asking, can they excite resonance of some of these features? This is 2 bridges in Bryce Canyon. And if so, what could be the outcome on crack growth and ultimately erosion of these landforms? And then the third, which was really unanticipated when we started, is this idea of public outreach. Some of these things that I showed you early on, like the animations and the sound experience, we found have been really fun to share. It's also like a nice positive message to share. Sometimes we get wrapped up in gloom and doom of, I don't know, geological engineering, landslides. It's been a positive and a fun message to share with people. So as I mentioned, this started with structural health monitoring. Again, you know, if we can establish this vibrational fingerprint through baseline modal analysis, then it's a simple approach to come back and measure those natural frequencies again. If they've shifted, that tells us that there's been a change in the structural composition of the feature. So this structural health monitoring has been around also for about 100 years. You know, they used to have these folks called wheel tappers in Victorian train stations, which would tap on the steel wheels of train cars and try to hear if they made a different sound. That's structural health monitoring through sound. And importantly, at the places where we want to and do measure, it has to be non-destructive. We can't go hitting on things. We can't use modal shakers. We can't install instruments permanently. We need to be able to come and set our instrument down and pull it away and not have left any trace that we were there. So for motivation, maybe some of you know, landscape arch lost a couple chunks explosively off the bottom of the lintel here in the early 90s. If you've ever been under landscape arch, which probably most of you haven't been, it's so cool. You can see the bite out of it where one of those slabs fell off. There used to be a trail that ran up under here, and you could sit in this alcove and look out at the landscape beyond, hence the name. But when this happened, the Park Service was faced with a challenge, is this safe to have this trail open? And ultimately they decided no, and they've closed the trail and it hasn't been open since. But you can imagine being in their position and and really, needing some information, right? Is it safe? Are cracks propagating? Is the arch going to fall down? And then also knowing, should I reopen the trail now? Is it safe? So these are some of the questions that that motivate us to basically put some data on the table for these land managers to be able to help them answer these questions. Just up the trail here from landscape arch is Wall Arch. Some of you might have known it before its demise. It collapsed entirely in the night of August 4th, 2008. And the trail used to run directly under Wall Arch. So had it collapsed during the day in August, there would have likely been people around and there really could have had a high probability for injuries or worse. So again, this concept should, or our approach is designed to be able to provide data into, some of these structural degradation questions that can ultimately be used maybe by, land managers to help keep visitors safe. This has seen us measuring vibration at some of the coolest places and some of the most amazing features in Utah. We work in arches, Canyonlands, Bryce Canyon. Of course, we work at Rainbow Bridge, natural bridges, and then all over Utah's public lands. There are thousands of arches in Utah, all of them different, all of them cool in their own way. And this concept of structural health monitoring relies on having an initial measurement. It's all relative. It is relative. You have to first have established baseline modal analysis. So that first measurement of natural frequencies and understanding what they represent. Once you have that, now you can come back and measure again and basically search for any frequency changes, permanent frequency changes. So here you see Rainbow Bridge. This is what we measured up here on the top of the bridge in 2015, I'm sorry. Same curve you saw from before. We went back in 2017, again in 2019, around the same season. Here, that's me measuring down at the base of the bridge. Again, the scale of the bridge is phenomenal. If you haven't been, you should really go. And basically, you can see here, the data are a little worse at the bottom of the bridge, but we can see that we're, tracking no frequency changes in these intervals. So that's good news. Nobody wants something to happen to Rainbow Bridge, right? And we're able to also to give this feedback to the park managers that say, within the resolution and the limits of our analysis, we don't detect any permanent structural change, adverse structural change in Rainbow Bridge over these intervals. These, were half a day of measurements. It takes longer to actually get out to the bridge and get back than it does to set up and do the measurement. So it's pretty simple once you've established the baseline modal analysis. And once this is archived, somebody can come back in 10 years, 20 years, 100 years and do it again. And there's no need to measure in the same spot as we measured whatever, just compare the data. So what we found though, along the way, is something that might look like this, and that we describe as reversible and environmentally driven drifts in frequency over time. Here you can see frequency. This is fundamental frequency of aqueduct arch. There's a main study site for Paul Geimer and his work. Plotting frequency versus temperature. It's air temperature in this case. And you can see a couple trends in this that Paul refers to as a check mark or a hockey stick form. The first is pretty plainly obvious. It is a direct correlation between frequency and temperature, where frequency increases as temperature increases. This is about a half a year's worth of data between February and July. This is a phenomenon we ascribe to thermal stiffening. So what's that? As the rock warms, it wants to expand. As it expands, grain contacts are squeezed tighter together, micro cracks close, macro cracks close, and in the net, the rock mass becomes stiffer. The elastic modulus goes up. And if we see here about a 10% change in frequency shown on this plot, that equates to a uniform, if it's uniform, change in elastic modulus of about 5%. So throughout the year, the actual, Young's modulus of the rock mass is changing by 5% or more. And this is something that we see everywhere in almost all of our sites. Here at Aqueduct, we have also this other interesting phenomenon where below zero, we now have an inverse correlation where frequency goes up as temperatures continue to drop. And this is something that we ascribe to ice formation in the pores of this sandstone. Now we know these aren't saturated, sandstone outcrops here. So this water must probably exist as like bound water on grain contacts and interfaces. And as it freezes, those little interfaces get in the net a little bit stiffer. And that results in an increase in frequency. So here you see, these are daily loops, and they go this way. So as temperatures begin to freeze overnight, we get this really rapid and instantaneous rise in frequency. And then as temperatures warm, frequency kind of stays steady for a while until that ice melts off at those tiny bits of ice must be at those grain contacts, and then frequency drops down. And it starts again the next day and the next day, and it changes a little bit from day to day. So we don't see this in all of our data. Very clearly demonstrated here at Aqueduct Arch. So the second topic was vibration risk assessment. And again, this is the subject really of Riley's work. Here you see on this image lots of things that people do in the Moab area in southern Utah. That people do everything out there. So this Yehu with his private helicopter landed on Pritchett Arch. He made quite a kerfuffle on the internet as he landed all over southern Utah. That's a $3 million helicopter. Obviously, that's something that nobody wants, right? That can't be good for the arch. This is Musselman Arch in Canyonlands off the White Rim trail or road. In the past, you used to be able to walk out onto these arches. Park Service doesn't want you to do that anymore. And you could say, well, okay, one person walking on the arch, well, that's probably not a bad thing. It's not good. It can't help the arch in any way. That's probably not a bad thing. And I think that's, what is that, 9 people? Yeah, it's 9 people on the arch. You can say, I don't like that very much, but okay. And then, okay, now we have a car on the arch, and people were driving their motorcycles across it a lot. So the point is, like, where do you draw the line? You say one's okay, 9, cars, no. The point is that, again, we need data for these questions. And so it's really our goal to add in some data that helps address some of these questions. Otherwise, on here, we see, and I'll come back to this, this was an induced earthquake in March of 2019 at the Bedrock Bureau of Reclamation Bedrock Injection Facility. If you don't know it, it's crazy. They take salt water from the Dolores River and they inject it thousands of feet underground because they don't want that salt water hitting the Colorado to make it too salty for agriculture. That's been going on for decades, and they've been inducing earthquakes for decades. This was their biggest. The facility was shut down for about 2 years after this. It went back online while they try to figure out how to fix this or what to do next. So I'll touch on that. And then this is Wilson Arch, right next to the highway. the question really is like, does being next to the highway with all these truck passes, could that somehow be adversely affecting the long-term structural stability of the arch? So these are tough questions. And they were really motivated by our work at Rainbow Bridge. And so there's a Native American consultation committee which advises the Park Service on management of Rainbow Bridge. And they had asked the question, can helicopters excite resonance of Rainbow Bridge? And we came in to do a study on that, but we weren't able to do everything we wanted. We couldn't fly a helicopter around Rainbow Bridge and sort of buzz it at it and do these crazy dives. We did a study at some smaller arches and Hoodoo's landforms. This is the same one in Bryce, where we could do some of this controlled flights. Probably you don't know, unless you've heard me yammer about it, helicopters generate infrasound from their main rotor. And it is, in fact, the strongest sound that they produce, but you can't hear it. It's at frequencies that are too low for you to hear. You might have like felt it in your body as a helicopter passes, or maybe your windows rattle in your house as a helicopter. That's infrasound. And again, it's the strongest. Here it's at 100 plus decibels for this two-blade Bell 206 helicopter. So when the frequency of this infrasound is very simply controlled by the revolution rate of the main rotor and the number of blades on the rotor. Super easy to predict, and then it's Doppler shifted as the helicopter flies around. So Bell 206 produces 13 hertz infrasound stationary. And then if it, Robinson, same, and so on. So when the natural frequencies of a given landform precisely align with the infrasound frequency produced from the helicopter, then we do get resonance, yes. We have measured that now in a number of places, and we get this rapid increase in vibration velocity as that happens. Now, individually, those are not very high, PGV, peak ground velocity events. But one of the questions that arose from that same Native American consultation committee was, okay, one pass isn't much. What about a decade worth of passes? And this is a really hard question. And what motivated us in working with Riley. So another thing we found, measurements over the years, here's Musselman Arch again, there's a seismometer on the arch, there's another one there, we have a reference just on bedrock over here. What we found is that arches shake up to 200 times stronger given an earthquake input than bedrock just there or just here. 200 times stronger. So like here's a record from a small earthquake. The black is the sensor on the arch, the red is the reference, and you can just visually see, it's a lot, it's amplified a lot. And then over here, you see amplitude spectral ratio, where we can see, that, okay, during this particular earthquake, it was amplified about 100 times at its natural frequency. So when the earthquake is able to excite resonance of the arches shake hard. What's the outcome? Well, one outcome could be that we have to pay closer attention to smaller earthquakes. Here's this paradox earthquake again from the injection facility. Magnitude 4.6, pretty far away. All these pink dots and red ones are arches. Reasonably far away, and the USGS kind of standard product is this shake map. And here you see peak ground velocity contoured. And so you can kind of use this to poke in on your site and say, well, it's like my site, saw something like, 0.05, that's centimeters per second. So that's not very high. But now, if you imagine that ground motion is amplified by 10 to 100 times, then these numbers can quickly grow a lot bigger. And now the question becomes, could any particular given event have been damaging at this arch, whereas I might not have previously considered it damaging? More questions. What about being near a road? This is Rainbow Arch, not to be confused with Rainbow Bridge. There's a backpack for scale. It's a very small arch. It was. Small but beautiful arch. It collapsed in the winter of 2018. There it is after the collapse. Before the collapse, it had just this really horrible looking crack running here in the underside of the lintel. Rainbow Arch was located just on this steep rubbly slope above the arch's visitor center, if you can picture that. And it's about 180 meters from the highway. Every time a truck passes on the highway, the arch shakes harder. We measured that bunches of times. One individual pass of a truck doesn't generate a very high PGV, but trucks have been passing by Rainbow Arch on this highway for 60 years. So, the question, our question was, did being near this highway somehow hasten the collapse of this arch? What's more, there's a railway right here. And this is a railway that carries radioactive uranium tailings from the banks of the Colorado River up to Crescent Junction. And it runs several times a week. So it's not some, defunct old railway. It also carries potash from the mines. So, and every time a train passes, actually the arch shakes hardest. That's the hardest thing that's the biggest source. So, the question was, did being close to the road hasten the collapse? That was a tough question. It required us to adopt subcritical fracture mechanics analysis approach, where we're looking at crack velocities. So we take like a given year and we ask, given the vibration environment in a natural, quiet place far from anthropogenic sources, what kind of crack growth would we predict in a year? And now, given the vibration environment from a anthropogenically noisy area like near a highway, what would we predict? And then what we show here is the ratio. So the ratio of rainbow, rain arch, that's our noisy spot. Aqueduct, that's our quiet spot. And so you see here the ratio. So this shows that in a year, a crack at Rainbow Arch, and this is a conceptual model after Rainbow Arch, a crack in Rainbow Arch would grow about 1% longer than if that arch were located in the wilderness by aqueduct in that same area. Okay, so that's not a lot, but it's also a value that compounds. So after 10 years, that 1% is more like 10%. And we're starting to, get to values that matter. So over long periods of time. We also asked, from our information data on helicopter flights, we said, well, how many helicopter flights in a year would it really take to really shake things up and cause a lot of damage to an arch? And, so this is the number of helicopter flights added, and this is the same crack growth ratio. And so, we're looking at, I think, this is 1 per day. This is 10 per day, it's 100 per day. And really at this 10,000 helicopter flights in a year level, we start to see really substantial increases in crack growth for a year, for just 1 year. So if you think that's a very high number, if you think it's absurd, then I beg you to look into what they're doing at the Grand Canyon in the helicopter corridor there and how many flights are actually permitted. It's not too much different from that. But nonetheless, this is the kind of question that we were asked in a management meeting, which at the time I stammered an answer that I didn't know. I couldn't tell them that information. So now we have, even though there's a lot of simplifications in here, we have the ability to come back with some quantitative results on that. We also added in an earthquake. So this is, we just took that year and took away the last 30 seconds that year and put in an earthquake with a given PGV. And these are moderate shaking events, so just 15 millimeters per second PGV, and that's generating a substantial increase in crack growth for an arch that experiences that event versus one that doesn't experience that event. And if it gets to 20 millimeters per second, our arch was finished, it failed. Okay, last topic, public outreach. That's me and that's Paul on Ouachimo Bridge, which is a natural bridges. Really beautiful, wonderful place. And of course, we have permits to be there. As I said, we didn't intend this early on, but we stumbled upon these ways of visualizing and letting people experience this dynamic and lively nature of these geologic landforms. It's been really a lot of fun to share that. We've had a couple of opportunities through the National Science Foundation, a short video. They invited us to this STEM Fest in DC to present. We probably talked to 10,000 kids over 3 days, and they, let them hear these sounds of arches. And this was a subwoofer that blows air, and so you can put a piece of paper in front and it shakes like crazy, and they're like that. Lots of this is a really media-friendly kind of project. Beautiful pictures. But to our benefit, we get to share this message that these arches are are lively, they're vibrating, they're sensitive, and they might, be a little more fragile than we think. It might, it's just not just this sort of massive rock object. If you know that each time you drive around, it shakes a little harder because it feels your car. If you know that when I walk there, it actually shakes harder because it feels me, we hope that this can kind of shift perceptions a little bit. And there's Aaron from one of our department open houses with some kids. We do this VR stuff with the online, with 3D models, and they kind of freak out. This is just a simple website we created and shared, and this all started actually at Corona Arch. That was the first place we measured, and we were looking to see if we could detect frequency changes using ears rather than eyes. And so MATLAB has this like simple one line, like create audio write, it was called, I think at the time, to create an audio file from vibration data. And so I tried it out, didn't work for that. But what I got instead was this like weird, cool rumble. And that's like what you heard at Barrette Arch when we started up. So at this website, it's very, dry. Everything's sped up 25 times. So this uniform speed up puts them all on the same page. Rainbow Bridge sounds low and powerful. Rainbow Arch sounds high and squeaky. And so you can just experience them as sound. Sometimes they're really beautiful, and sometimes they're not. I was recently out at one of Utah's most beautiful arches called Colonnade Arch. Just incredible arch, but as a sonic experience, not so beautiful. So it's really interesting, and we don't know what we're going to get when we go out measuring. So this is something that we describe this transformation between a vibration fingerprint to what becomes kind of a sound print. It's just unique to every landform. The set of resonant frequencies is unique, so the sound is always different. And again, it's just this really kind of new way to experience landforms, and which has led to us several really cool opportunities to work with artists over the years. We worked with a Danish sound artist, Jakob Kierkegaard. He produced a sound piece which was on display at Dartmouth's Hood Museum. You can actually hear it online. Really amazing piece. It's so simple. He just took vibration sounds from Rainbow Bridge and elsewhere and mixed them with ambient audio recorded on site. So very normal stuff like a fly, a breeze, a creek that you're used to, and it gives you this immersive feel. But then you experience this other audio, this thing that's also very real, but not something that we're used to experiencing. We don't have the senses to experience this vibration. It doesn't mean it's not real. It means that our senses aren't tuned to that. So a really unique piece, very simple. We also recently worked with Utah's own Terry Tippis Williams. You might know as a Red Rock advocate, wilderness advocate. Terry lives in Castle Valley. If you know her, you know that piece of information, or if you've read her writing, you know that piece of information. And when we did our study on Castleton Tower, it really resonated with Terry. So we helped advise, provide input on a piece called Resonance of Stone, which is in her book, the paperback version of her book, Erosion. And then she reads it for Patagonia and was on their website. Currently, we're working with photographer Fazal Sheikh. Fazal is a portrait photographer, and he turns his lens to the ground from time to time as well. And Fazal has been focusing on these kind of landscape portraiture of the Bears Ears region. And he created this installation, which was at University of Chicago, and it's currently at Yale, whereas there's this frieze of images on the walls. And the center in this podium is a offering from Navajo spiritual advisor, Jonah Yeoman. And then this little octagon bench here has a speaker system which plays some of these vibration sounds from landforms of Bears Ears. And it's both like audible, but also tactile. If you sit on the bench, you can kind of feel this. So these have been really fun, motivating, totally unanticipated. And with that, I'm going to close it out. Big thanks again. And then we have a website here where a lot of the media stuff, those various websites are linked. So thanks.